Okay. Today I present one algorithm to solve spline interpolation. Take a review. We first specify an infinite sequence of lots. Then we define basic spline function of degree 0 by this expression over this interval from ti to ti plus 1. This function is equal to 1. And when x is not in this interval, the function value is 0. This is the starting point to define basic spline functions. For k greater than 0, then BIK definition is this. If I rewrite the second term into this and introduce this special linear function, then the definition can be written as the written in this elegant form. Okay, yeah, this is the definition of basic spline functions. Basic spline functions have many nice properties. Let me make a list of some of the properties. First, BI0, B spline functions of degree 0. This function is non-zero only over this interval. This interval is called the support of this function, and it is 0 at other points, not in this interval. For BIK, when k greater than 0, then the support of this function is this interval from ti to ti plus k plus 1. And on this interval, this is the interval that we are interested from t0 to tn. We have infinite many basic spline functions, but only the following are non-zeros over this interval. Yeah, only these spline functions non-zero on this interval. This is the interval that we are interested. The third property is the sum of all the spline functions of degree k is equal to 1. This sum looks like an infinite sum, but actually it is a finite sum because for x physics, only a finite number of the terms non-zero. So actually this is a finite sum. Property D, BIK, very smooth. It is in this space, smooth of order k minus 1. The last property, for this space, retreat the function in S and K to this interval. For this space, a basis is, this is a basis. Yeah, when I is k minus 1, this is a, I is negative k plus 1, and so on. I is n minus 1 k. Yeah, a basis for this space. Yeah, but this basis has nice property. Okay, very nice property. At least the sum of these functions is equal to 1. Now this is our review about basic spline functions. Now I present one algorithm to compute, to solve spline interpolation. Topic one. Spline interpolation. Given a table of function values, given a table, x, y is equal to f of x, x0, x1, x2, and xn. Function value at x0 is y0, y1, y2, and yn. Okay. Y is equal to f of x. Yeah. Now, we want to find a spline function from S and K, so that S at the loops xj is equal to yj. Okay. Yj. Here, let me change this n to say to q. Okay. Q is different from n. So j here is greater than 0 or less than or equal to q. Okay. About these logs, let me make one assumption. Assume the logs all in this interval. Okay, all in this interval. Okay, now how to find, such as use this property. Okay. This is a basis for this space. So S is from this space, we can express S as the following linear combination. This is a summation, say L from negative K to N minus K. Yeah, use this basis. I between negative K and M minus K. These functions is a basis, form a basis. So some scalar, some number, alpha L, then times B L K X. Okay, where I assume, we assume X also in this interval. Because I assume X is in this interval, so restrictive function the value at X is equal to the function f at X, because X, I assume X is in this interval, so we have this equation. So therefore, any function from S and K, when X is in this interval, function value is the same with the original function. So we have this equation. Okay, now the next question is we need to determine the coefficients alpha L. How to determine alpha L? Use these conditions. Plug in xj in X. Then we have a linear system. Plug in xj in X. Then we have alpha L B L K Xj. It is equal to Yj. Where J is between 0 and Q, right? J is between 0 and K and Q. Yeah. Plug in Xj in X here. Then we have a Q plus 1, from 0 to Q plus 1 equations. So we have a linear system. So we have a linear system. Okay, if I write this linear system in matrix equation, then the linear system, this linear system is A is a B negative K. Yeah, L from negative K to N minus 1. K X0 B negative K plus 1 K X0. The first row corresponds to the first equation when with J being 0, right? So this is a B M minus 1 K X0. Yeah, first row. Now the second row corresponds to J is 1. Second row is a B K X1 negative K plus 1 K X1 B M minus 1 K X1 and so on. The last row, the bottom row, corresponds to J being Q. Negative N minus 1 K XQ. Yeah. This is the coefficient matrix. How about the unknown X? The unknown X is a vector of the unknown alpha. X is the unknown alpha. When L is negative K, so the first entry is a negative alpha, negative K. When L is negative K plus 1, alpha negative K plus 1, and so on. Then the last entry is L is N minus 1. So alpha N minus 1. This is the unknown. How about the right side? B. B is when J is 0, Y0. When J is 1, Y1. And when J is Q, YQ. Yeah. Yeah, solve this linear system. Then we have alpha. Take a look at the entries of the coefficient matrix. By property, by this property, spline functions are non-negative. So we have entries of matrix A all are non-negative. All are non-negative, this matrix. And second, by this property, by property B and C. Property B says that when x is in this interval, only these functions are non-zero. So property C says that sum up all the B splines, the sum is equal to 1, but only these functions are non-zero when x is in this interval. Then actually left side is a finite sum, summation I from negative k to m minus 1 b I k x is equal to 1. Okay, when x is in this interval. Okay, now here, because I assume all the loops are in this interval. Therefore, the sum of all the entries in each row is 1, actually. Row sum, yeah, row sum of A is equal to 1. Yeah, this coefficient matrix, all the entries are non-negative, and row sum is equal to 1. In other words, the entries in this matrix, they are about at the same size. Their magnitude, absolute value, about the same, okay, in the same order. Okay, it doesn't like power basis. Power basis, xk, right? Xk, yeah, xk may be very large, but in this coefficient matrix, all the entries are about the same size. Yeah, so as a result, A, this coefficient matrix is, we call it well conditioned, not sensitive to round-off error. So if we solve this linear system for the unknown alpha, the solution should be accurate. Okay, this is a spline interpolation. This is the problem about spline interpolation. Okay, now next step, we need to compute the entries in this matrix. After we compute the entries of this matrix, then we have a linear system. Then solve the linear system, we have alpha. After we have alpha, then we have this spline function. This spline function interpolate this table. After we have this spline function, then we can compute function value at some x. Specify 1x between t0 and tn. Then compute function value. Now the next step is how to compute first. How to compute the entries in this matrix. And after we get alpha, how to compute s and x. This is the next question. To answer this question, I first introduce one approach to compute a function of the following form. Okay, an approach to compute a function of the following form. Okay, which form? Yeah, this form. A summation I from negative infinity to infinity. Yeah, Ci X. What is CIK X? It is from the user, okay, from us, okay. Say for example, if we specify CIK, CI, say CIL, no, if I specify CLK X is equal to 1, and CIK X is equal to 0 when I not equal to F, then this function is equal to BLK X. So if we know how to compute the value of capital F, then we know how to compute BLK X. And also, this is an example 1. Example B, if I specify L is negative K. If I specify C negative K, yeah, this coefficient is equal to alpha negative F, negative K plus 1 K X be alpha negative L plus 1, and so on. How about the last L? The last L is n minus 1. CL minus 1K is alpha L minus 1. Then the other CIK in this expression 0. Then F is equal to summation I from negative K n minus 1 alpha I BIK X. Then this is this function S. So now let's solve this problem. How to compute capital F upon X. If we know how to compute capital F upon X, then we can compute all the entries in this matrix. And also we can compute the value of S at X. Okay, now let's see how to compute capital F at X. This approach the approach to compute capital F at X is to reduce capital F to a function that only involves BI0, because a BI0 definition is simple. BI0 is equal to 1 over this interval, and it's 0 at other points. In the definition of capital F, the definition involves BIK. Now, I reduce BIK into BI0 by definition of BIK. What is BIK? By definition, BIK is this. Okay. Now I plug in this equation in BIK. Actually, this is a lemma. Yeah, let me present this lemma first. Lemma. Okay. Let alpha x any function be given. Okay. I is 0, positive or negative 1. Yeah. So this index ranges from negative infinity to positive infinity. Okay. Be given. Okay. Be given. Okay. Then summation I from negative infinity to positive infinity, alpha I. Yeah, this alpha is this alpha. BIKX by definition of BIKX. We have what is the definition? Yeah. Yeah, this is a V I K X B I K minus 1 X. KX. Yeah. Actually, this is a finite sum. Rearrange the sum. Okay, rearrange the sum. Then we have combine the terms, the like terms. Then we have this equation. Alpha I x V I K x alpha I minus 1 x 1 minus V I K x, and then times B I K minus 1 x. Yeah. Yeah. Actually, this is a finite sum. Expand the sum, rearrange the terms, then we get this equation. Now, I apply this lemma to capital F. Okay, by this lemma, then capital F by definition is this: I from negative infinity to infinity. CIK, this function is from us. Suppose we know CIK times BIK. In this definition, the definition involves BIK. Now, by this lemma, then I can write this infinite sum as this: I from negative infinity to infinity. CIKX. Yeah, alpha I is CIK. Then times VIK X plus alpha I minus 1 is CI minus 1 K. I minus 1 K X. Then times 1 minus VIK X times BI K minus 1. Yeah. So definition for capital A involves BIK. Now, by the lemma, I can reduce BIK to BI K minus 1. Okay. Okay, now I said this part, I denote this part as CIK minus 1. Okay. Yeah. In other words, define CIK minus 1 X as CIK VIK X plus CI minus 1 K X K X. According to the definition of V, what is VIK? VIK, where VIK? Let me see. Oh, VIK is equal to X minus TI over TI plus K minus TI. Then I plug in the definition for VIK and simplify the expression. Then we have X minus TI CIK. Yeah, VIK replaced by this plus TI plus K minus X CI minus 1 K X. Then over TI plus K minus TI minus TI. Okay, CIK minus 1 is this. Therefore, capital F is summation CIK minus 1 times BIK minus 1. So capital F is equal to summation I from negative infinity to infinity CIK minus 1 X. Okay, now I apply the lemma again. Apply this lemma again. Then I can reduce BIK minus 1 into K minus 2. CIK minus 2 X. Definition is here. Yeah, replace K by K minus 1. Then here, K minus 2. And then this is a BI K minus 2. And so on. Continue the reduction process. Then eventually, we can express capital F in terms of BI 0, CI 0, BI 0. The definition of BI 0 is simple. Now, how to compare capital F at x. Okay. How to compute capital F at x? Okay. Give me an x. Okay. The first step is, okay, find some interval, say Tm plus 1, that contains x. Give me an x, then I look for an interval, say Tm plus 1. This interval contains x. Okay. Then, after we load this interval, then capital F summation I from negative infinity to infinity, Ci 0 x, Bi 0. Okay. Now I expand this sum. Cm when I is m, Bm 0 x, and then the next term is a Cm plus 1 0 x, Bm plus 1 0 x, and so on. And also on the left side, the next term on the left side, m minus 1 0, b m minus 1 0 x plus. Yes, there are infinitely many terms, but only this term non-zero, because x is in this interval. Bm minus 1 0 is equal to 0. Yeah, Bm minus 1 0 is equal to 0. So actually, this is a B, a C m 0 x, Bm 0 x. But Bm 0 x by definition is equal to 1. So this is a Cm 0 x. So how to compute capital F for an x? Step 1, determine interval that contain x. Then the value of capital F is Cm 0 x. Okay, now the next step is determine Cm 0 x. We use the following triangular array to determine Cm 0 x. Okay. Keep this in mind. X is facet. Okay, facet given to us. The original F, Ci k. We load this. Okay, we load this. So the first column of the array is a Cm k at x. We load Cm k. Cm minus k x below it, and so on. Cm minus k plus 1 0 x. C 0 m minus k at x. So the first column, because below ck, so first column below. Then compute Cm k minus 1 at x. How to compute Cm k minus 1 at x? use this equation. Use this equation. When k is m, we can compute c m no k I is m. Okay. ck we know, so we can compute ck minus 1 by this equation. So ck minus 1 m below it from this number and this number, we can get this. And also from this number and the next number, we can get cm minus 1 k minus 1 x, and so on. Cm minus k plus 1 k minus 1 x. After we know ck minus 1, we can compute ck minus 2 m. Yeah, by the same formula. Replace k with k minus 1, then we get k minus 2. Here is a cm minus 1 k minus 2, and so on. Yeah. Okay. In this way, we get cm1 cm minus 1 1. Then from cm1 cm minus 1, we get cm 0 0. And cm 0 is capital F, the value at x. All right. This is an algorithm to compute capital F. To compute capital F. Okay. Now, with this approach, then we can compute all the entries in the matrix A. Say, for example, let me compute this entry. The entry is, let me see, matrix A, the 1 1 entry. Okay. Say, for example, compare the 1 1 entry. Yeah. How to compute this entry? Okay. Step 1, number 1. Determine an interval Tm plus 1 such that the root x0 is in this interval. And then step 2, capital F. Let me see, capital F. This is a capital F. Now let me capital F, original definition. Okay, now let me specify CIK. Okay, CIK. In the definition of capital F, specify CIK. CIK. When I is negative k, CIK is equal to 1. The other CIK 0 when I not equal to negative k. Okay, yeah. Here. Then capital F is B negative k. K. Okay. Then capital F is equal to B negative K, K, X. Okay. Now, by this triangular array, okay, then by the triangular array, okay, we can compute f of x. F of x is CM0x, but this is equal to B negative K, X, where X, what is X? X0, X is X0, X0. Similarly, we can get the other entries. So we have matrix A. After we have matrix A, we can solve the linear system. Yeah, the linear system has infinitely many solutions because the unknown, how many unknowns? Alpha L, how many unknowns? L from negative K to N minus 1. So N minus 1 minus negative K plus 1. So many unknowns. This is cancel 1 N plus K. So many unknowns. How many equations? Q plus 1 equations. Yeah. If number of equations less than number of unknowns, there are infinitely many solutions. Okay. So solve this linear system, we have alpha L. After we have alpha L, we have the spline function. After we have spline function, we can compute the value of spline function at any x. How to compute spline function at any x? Because spline function is a function of this form. Specify CIK as the alpha. The alpha alpha L actually, yeah. Specify CIK as alpha L. Then this capital F is equal to S of x. X is fixed. How to compute S of x? First, determine an interval that contains x. Then use the triangular array to compute the value of capital F. Capital F now is S, the value of S. Yeah. So this is an outline, okay, about the algorithm. For the details, you can take a look at my notes. Then I finished these two sections, 6.5 and 6.6. The next class, I will here. So far, we have used polynomials to interpolate a given table of data. But actually, there are other type interpolations. We can use other functions to interpolate a given table of data. So in the next class, I present one other type of interpolation using other functions, not polynomial. And then after next class, we turn to study chapter 7. Chapter 7, we study how to numerically compute derivative and how to numerically compute integral. Okay. Yeah, let me stop here today.